Hi everyone, so welcome. I'm Geethu and I'm a solutions architect from Ivan. So today my goal is to take you through 40 minutes talk about a practical guide to picking a vector strategy for production AI, how to choose between different databases, so basically my aim is to give you a framework to choose a vector strategy or a vector database that will suit your use case or your requirements. And I'm joined by Vadim from Steadforce. He is going to give you a quick overview of a real use case that he has worked on where this framework could be applied. Now, before we dive in, a quick introduction about myself. So like I said, I am a solutions architect at Ivan. So basically my day job is to design data platforms on Kafka, PostgreSQL, ClickHouse, or OpenSearch, or other open source services. So I basically help different companies build their data architecture based on these services. And my background is that I worked as a data integration developer before, and I did a master's in data science as well. So this is my first official talk, so if I'm a bit nervous or if I look into my slides a lot, that's because that I am really nervous and tense. So thank you. So yeah, outside of work, I love books, movies, and I love traveling as well. So if you want to chat about any of those out after the talk, I'm happy to. All right. Now I'll hand over to Vadim.
Thank you. So good evening, everyone. My name is Vadim Rastov, and I'm a senior data scientist at Steadforce. So we are a partnering company of Ivan. And basically, I'm building end-to-end machine learning and Gen AI pipelines in cloud or locally. Talking also about my background, I also studied data science, finished LMU at Munich, and my hobbies are also traveling. So if you need any hints or like tips what to do next, where to travel next, just come to me. Yep.
Okay. So I want to take you through our Ivan platform. So Felix already gave a really good pitch about what Ivan does and how everything works there. So I just wanted to give you a quick overview of what Ivan is and how it is relevant to my talk today. So as you can see, what we do is we provide a dozen of open source services like Kafka, PostgreSQL, OpenSearch, Valkey, or ClickHouse, and many more as managed services. So basically for our customers, what that means is that they don't have to worry about managing the databases. They don't have to worry about the operational complexities behind it. They can just run it and use it. For me, what that means is that I get to see how similar workloads behave in different databases and different use cases and across different customer environments. So basically, that's the unfair advantage that I'm bringing to this talk. And to be upfront, I don't have a preferred solution or preferred service. Basically, we run all three of the services that I'm going to talk about, so there is no preferred answer for me here. Now, to build the talk or to make this a bit concrete, I'll anchor everything to a scenario. So suppose you are building a product search engine for an online shop. So a customer uploads a photo of a sneaker and asks, find me something like this. It should be under 100 euros. It should be in my size and it should be in stock. So the initial prototype is simple, right? So you can have around 1,000 products. You embed these with OpenAI, store it in Postgres. Then you can query with pgvector. It works great, and you ship it. And then you go into production, and then the reality hits. So you have scaled up. You have around 5 million products across 200 different categories, and you have multiple filters now. So that's when you see the problem, and that's when the question arises on which database to use here. So you see latency spiking, recall dropping? So that's the question that we are going to answer today. So my goal is to talk about 3 databases, 3 trade-offs, and 1 framework to choose from them. So I'll be talking about how these databases index vectors, how they handle metadata filtering, and how much memory they need, and when each one of them breaks down. So before we dive into the databases, quick refresher on vector search and embeddings and vectors and terms around it. So what is an embedding? So each product, it can be a list, it can be an item, description, image, it can be anything. It gets converted into a list of numbers. So that's a vector. So for example, red Nike Air Max will be converted into 0.12, negative 0.34, 0.78, around 1536 numbers if you are converting that into a vector space of 1536 dimensions. So basically you are converting images or data into numbers. Those numbers doesn't make any sense to us. It makes sense to the machine, but it doesn't make sense to us. Now, why does this help? So similar products will have similar vectors, so they will end up as nearby points in the vector space. So when you're doing a vector search or a similarity search, you are finding the nearest neighbors to your query vector. You're not finding the exact answer, you're finding the similar answer there. So similar idea, just a different example. So you take the input, the cat sat on the mat, you embed that with either BGE base or OpenAI or MiniLM, depending on whichever embedding model that you want to use. You embed that and then you convert that into a vector. Now, 3 things that you need to remember here. So similar, if this query has similar meaning, it will have close vectors, or like if the product has similar meaning, it will have close vectors. So red Nike and Crimson Air Max, so 2 different queries, none have same words, but it will have similar answers, or it will be close in the vector space. And the second thing that you need to remember is that the length of the vector space or the vector dimensions is fixed by the model. And the third thing is you don't mix models in the same index. So if you have half of the database embedded with BGE base and the rest embedded with OpenAI, then you can't mix that and use it, because basically it's going to be a garbage thing. You can't search within that. So the whole concept is you're going to find by distance, not by equality. So everything else in this talk is engineering. Now, when it comes to search, there are 2 terms. So we have exact search and approximate search. So exact search means that you compare against every vector in the database, and then you get the exact answer, you get the correct answer. So you get the correct answer, but it's going to be slow, especially if it's above 100K, or like if it's a really huge database or huge data volume. That's where approximate search comes into play. So ANN, or approximate nearest neighbor search, what you do is instead of comparing with all the vectors in the database, you use an index and then skip 99% of the database and then search within the rest of the data. So you won't get the exact answer. So if you're searching for the top 10 products, with exact search you'll get the exact top 10 products. With the approximate search, you'll not get the exact 10 ones, but you might get 8 or 9 or 7, depending on the algorithm that you're using and depending on your database, how the indexing works and everything. So it's slightly inexact, but it's much faster. So that's what you usually use for production. So the trade-off that we have with using approximate search is recall. So what fraction of the right answers came back? And recall is how we know approximate is good enough. So if you, a formula for recall for the top 10 products is that recall at 10 equals intersection of true top 10 and index top 10 divided by 10. So to explain it in simpler terms, so if you have exact 10 products, so if you're searching for the top 10 products, you'll get exactly, if you use exact search, you'll get top 10 correct answers. Whereas if you use approximate search, you'll get 10 answers, of which 9 might be correct. So you divide, so how much of a number is accurate, you divide that by 10 and then you get the recall. So in this case, if you take the sliding scale, so recall at 10, if it's 0.50, basically that means 50% of the data or half of the returned answers were inaccurate, so we can't use that. So basically for RAG applications or retrieval augmented generation applications, you want it to be between 0.85 or 0.95. If you get a recall of 1, basically that means you are using exact search, not ANN.
Just here to make you nervous.
Yeah.
No, don't touch it at the bottom because this is the sender and then it will run out.
This,
Touch it here.
okay, well, thank you. Now, so in ANN, there are two algorithms that you usually run into. So HNSW and IVF flat. So HNSW is hierarchical navigable small world. So think of it like a postal hierarchy. You want to find a house or postal address. You can go from country to city, and then from city to the street, and then city, street. From street you find the exact house that you're looking for. So basically you start at the top layer, you go into the next layer, find the closest answer, you go to the next layer, go find the closest answer, like that until you reach your final answer. So the query speed is going to be fast, but it has a trade-off with slow build time and it requires more memory as well. The second algorithm that you'll run into is IVF flat or inverted file with flat compression. So it's similar to sorting books by genre. So if you want to find a particular title in a horror genre, you don't have to look through the entire library to find that particular book. You can just go to the particular bookshelf where this genre resides. So like if you have sorted it by genres, and if you have a horror book shelf, then you can just go to that particular shelf and find the book. So that's basically what IVF flat does. So it divides the vector space into clusters. It finds the closest cluster and then find the answer from there. So basically, boots will be in a single cluster. Red shoes will be in a cluster. Then sneakers will be in a different cluster, like that. So you divide the vector space into different clusters and find the answer. So the trade-off here is that the query speed is going to be slower. The build time is fast and the memory usage is less, but the query speed is going to be slower. Now, to show you visually what I was talking about earlier about the two algorithms. So HNSW, the query vector enters at layer 2, then it finds the closest vector, then goes to the next vector, it zooms in onto the next layer, then finds the closest vector and goes to the final layer and finds the right answer. So you start at the sparse layer and then go deep into that. Whereas in IVF flat, it's going to be divided into clusters, so you can see in this example, you can see 4 different clusters. So the query vector is going to see which centroid of the circle is the closest one, and then within that particular cluster, it finds the answer. So basically, you reach at the same destination, but you use different journeys or different path. Okay. Now that the basics are out of the way, we'll go to the three databases. So we have I'm talking about three different databases today. We have PostgreSQL plus PG vector, so where the vectors are going to reside next to your transactional truth. So PostgreSQL is an OLTP first engine. So embeddings are going to live next to the data that they describe. Then you have ClickHouse, where the vectors are going to reside next to your analytics. So it's a ClickHouse. If you are not familiar with ClickHouse, it's an OLAP first engine, so it's an analytical database. So embeddings are going to sit alongside billions of rows that you already aggregate, or you have some other aggregation function. Then you have OpenSearch, where the vectors are going to sit next to your text. So OpenSearch is a search first engine. So KNN, it's going to sit next to BM25 filters for setting or highlighting the different features that a search engine will use. To dive deep, so let's start with PostgreSQL plus PG vector. It's basically the don't add another database option. So like I said, it's a PG vector is an open source extension. So you install it like any Postgres extension. You will get you will add three things. So you add a data type called vector. Then you have two index types, HNSW and IVF flat. Then three distance operators that will let you write queries like order by, embedding, distance, limit, like that. So basically that's what PG vector does, and that's it. That's the whole thing. So that's the most simple thing that you can use for a vector search. So the big reason to choose this is if you already run Postgres, you don't take on a new system. You can keep on using the same backups, same monitoring, same security model. You have already a team working on, so you don't have any other additional operational overhead. So there's no new thing to learn here. The second database, that is ClickHouse. So it's like I said, it's a OLAP. It's a analytical powerhouse that does vectors. So it's a column-oriented database. The vectors are going to sit just as an array. So it was designed for billions of rows of events, logs, and metrics. And the vectors are stored as array of float 32, and then you can add a vector similarity index. So the thing that makes ClickHouse unique or good for vector search is that it handles filters differently compared to other engines. So it does pre-filtering. So before doing the vector search or the similarity search, it applies the filters that you gave in the query. So if you have some rare conditions, then it will apply those conditions first before doing the similarity search. And finally, OpenSearch. So it's a distributed search platform with vector search via KNN plugin. So it's open source version of Elasticsearch. So it comes from it's a fork of the Elasticsearch model, if you're already familiar with that. Now, so the pitch here is that it does hybrid search. So it does both vector search as well as keyword or lexical search. So if retrieval is your product and it's the core thing that you want, then OpenSearch could be a good answer for you. Now let's go back to our initial analogy or initial example. Okay, so our level 1 is find similar sneakers. It's easy. It can be done in all the databases. Then you go to the level 2. You add more filters. So you say under 100 euros, it should be only shoes. Most DBs still handle that. So you have around 2 metadata filters, and 30% of the whole database matches the query. Now you go into level 3. When you scale up, you go into level 3. So you add more filters. So you have a highly selective query. So basically the recall is going to be dead in this case. And why is the metadata filtering is one of the problems that we face in production. So that is the level 3 issue that we saw earlier. So you have 5 different filters and you probably think it works, but it might not. Now, metadata filtering is where recall goes to die. So the problem here is that the ANN index that you built is built on the whole data set. It's all built on the full data set. If you apply filters on top of that, it changes the effective data set. So the index assumption breaks, and that is when the recall drops. So if you have a query that filters more than, or you will get only 2% of that output, and if you want to run vector search on that, then that basically means you are running the query on a very small data set. So we have 2 different strategies on how to address or how to handle the metadata filtering. So you have post filter and pre-filter. So each database that we are talking about today, they have their own default ones, or they can be tuned in different ways. So what does pre-filter and post-filter means? So post-filter is you search first and then you filter later. So if you're looking for a book or a particular title, you search the whole thing and then you throw away the wrong genres. Whereas in pre-filter, you filter first and then you search less. So you go to the right section first and then find the best match. So the problem with post filter is that if only 1% of books match your genre filter, then the top 1,000 results, it might contain 0 useful results. So that's why pre-filter it sounds better, and it is better when the engine supports it efficiently. But not all of the databases support that. And ClickHouse does this naturally because of its columnar storage. The others will have to bolt it on. Now, how each database handle filtering? So for PostgreSQL, the default strategy is post filter. So if you have selective filters, the recall is going to degrade. Then you have ClickHouse where it's pre-filter, so it's best in class, or like it will perform better for metadata heavy queries. And then you have OpenSearch. It does handle both post filter and pre-filter, but by default it's going to be post filter, and it's generally good, but it can surprise you. Now, since I'm talking, my example is on e-commerce, I just want to specify that it's not just a problem in e-commerce. It can be in multi-tenant SaaS, or if you're searching by a particular tenant ID, or it can be in a scenario where you have compliance and access control, like you want to filter by department, clearance, and document status, or if you have a time scope retrieval, like you want to filter out candidates after a particular date. These are all scenarios where you can find this problem. Now, so I'll just show you how the query looks in the 3 databases. So in PostgreSQL plus PG Vector, I assume it's mostly familiar to you, so because it's SQL, so it's simple. If you already know SQL, you can keep on using that. And then you go to ClickHouse. ClickHouse query also looks similar to Postgres one. It's similar to SQL, but if you look carefully, there are some differences. So so here you can see that the distance is we are adding by a function call here, not as an operator as in Postgres. And then if you look at the where clause is going to be executed first, and then, or like the filter is evaluated before the before the vector scan. Then you go into OpenSearch. The query does not look like, it's not SQL, or it does not look like SQL. It looks mostly REST and JSON, so it's a different style. You post to the, for example, in this case, you post to the product search endpoint, and you have two different parts. You have filter, and then you have must close where the vector query resides. I just wanted to show you how the query looks different. So what I did is I did a performance test between three databases. So I want to show you how it differs in the three databases. So what I did is I took the same workload, so 500k vectors on a 768 dimension vector space, and I used that in three different databases. So PostgreSQL, OpenSearch, and ClickHouse all were deployed in the same instance type or instance specification. So 32 GB RAM, 8 vCPU, and it was on I1. Like I said, I1 provides these services as managed, these open source services as managed services. So I chose I1 to deploy the services. And what we are comparing is how each engine uses this budget. All right. So if you do a quick scan of the table, PostgreSQL has slow and memory-heavy index build, but it has it fits in shared buffers, and it behaves well below like 10 million vectors. Then you have ClickHouse that has fast bulk ingest, and it has ANN or brute force on filter. And then you come to OpenSearch. It has an online tunable build, and it comes with its own hybrid pipeline. It has built-in score normalization, but it uses off-heap phase. So before I go deep into the next section, why does vector dimensions matter? So like I said, I'm using a 768 dimension space here. So if you use different models, you get different vector space, all right, vector dimensions. So if I use 768 dimensions as a baseline, and if you downgrade to a 384 dimension space, then the memory and latencies are going to be halved. And if you scale up to a more diverse dimension space like 1024 or 1536, the memory and latency is going to be it's also scaling roughly linearly in that direction. So I just wanted to show you how vector dimensions matter when it comes to a vector search. So for this scenario, for this testing purpose, I used a 768 dimension space. The first thing I tested was memory footprint. So memory footprint was around 6 gigabytes for PostgreSQL. The index was shared in shared buffers and OS cache, but the memory used was around 6 gigabytes, and for ClickHouse it was much lower. It used around 1.2 gigabytes. It was compressed on disk, and it uses columnar, so makes sense. Then you have OpenSearch, where it used around 3 gigabytes of storage, and it had also around approximately 4 gigabytes of JVM heap space as well. Now the third thing I measured was query speed. So if you can see, ClickHouse did better, so it returned my results within 30 milliseconds, and then PostgreSQL and OpenSearch, it had both around 55 milliseconds. So depending on the use case, or depending on the algorithm that you're using, the query speed differs. And the next thing I measured was recall under filters. So For ClickHouse, it returned me around like 95% of the answers returned were accurate or exact, and for OpenSearch was also comparable, like 0.92, and then PostgreSQL was around 0.78. And then you go into horizontal scalability. So how does the scaling work in different databases? So PostgreSQL, it does beautifully in vertical scaling. You can add more storage and stuff like that. But for horizontal scaling, you need to use read replicas or you need to use other extensions. And for ClickHouse and OpenSearch, it uses native sharding. So it can scale horizontally better. Then PostgreSQL does better around 100 million vectors, and ClickHouse and OpenSearch can handle more than that. Then the complexity ease of use is for lower for PostgreSQL, and ClickHouse is medium. OpenSearch has a medium to high complexity because of the because OpenSearch since OpenSearch has added operational complexity due to the heap storage and phase. Now, the final scorecard. So operational fit PGs does fit better, and then for hybrid search quality, open source it's purpose built for hybrid search, and ClickHouse is kind of weak in lexical search. Then scale ceiling, so Postgres cannot be, it needs additional complexities for scaling horizontally. And for recall and filters, ClickHouse does better because of the pre-filtering like I discussed earlier. And for ecosystem maturity, or like Postgres is familiar to most of the people, so it is a better option there. So my honest opinion is PostgreSQL wins on operational simplicity and OpenSearch wins on retrieval features. So if you have a retrieval as the product, then OpenSearch, or if you have a huge data volume and if you want to win on filtered scale, then ClickHouse wins. Now, the decision framework, or how do you actually decide? So 3 questions actually matter. How many vectors do you have, or like how many do you expect in 12 months? The second question, does your query combine vectors and metadata filters heavily? And the third question, how much operational overhead can your team absorb? So the decision tree, so where does the retrieval needs to live? So if you want to live in the same transactional boundary or in the same transactional database as your app data, then go for PostgreSQL and PG Vector. Or if you want it to reside in alongside many of the analytical queries on a columnar storage, go for ClickHouse. And if retrieval is the product, and if you want hybrid search, then go for OpenSearch. Or if you have more than 100 million vectors or billions of vectors with hard recall or latency SLAs, then go for a dedicated vector database. And if you answered no to any of these questions, start with Postgres plus PG Vector and migrate later if you want. So the most underrated factor in any database decision is the best vector strategy is the one that doesn't add a new system. So you can be an architecture astronaut and you can evaluate 4 to 7 different vector databases, run benchmarks for 6 months, or you can be the engineer who sleeps at night because they use PG Vector because we already have Postgres, and you can migrate if it hurts. So if you're already running Postgres, PG Vector first. If you're already running ClickHouse, you add vectors there. If you're already running OpenSearch, you add KNN and use vector search there. So this is my opinionated scale thresholds. If it's less than 1 million vectors, use PG Vector, no questions asked. For 1 million to 5 million vectors, PG Vector with HNSW, but you have to tune carefully to make sure that you don't lose any recall or you don't lose any precision. Then if you have more than 5 million vectors, then you evaluate ClickHouse or OpenSearch. And if you have more than 50 million vectors, you use ClickHouse, especially if you have an analytical use case, or you use a dedicated vector database. And if you have billions of vectors, go for dedicated vector database like Quadrant, Milvus, or VVA. So one more reality check before I wrap. So the operational overhead is going to be minimal for PG Vector. It's going to be medium for ClickHouse. It's going to be really high for OpenSearch because it has JVM tuning, shard strategy, and you need to be mindful about all of these. So if you don't have time to maintain a sports car, don't buy it basically. So whatever you can use, whatever works, use that. So what you should remember tomorrow. If you use PG Vector, start there, symbol, 0 overhead. It's great up to 5 million vectors. Then ClickHouse, go there when metadata filtering gets hard or gets complex and scale gets large. Then you go for OpenSearch when you need hybrid search, or you already run an OpenSearch, or you already have a similar search engine in use. Then metadata filtering is one of the production problems, and pre-filter beats post-filter. And dimensions, or the vector dimensions, it drives memory, so you plan capacity around your embedding model, not the number of vectors that you have. And start symbol. If you don't use any of the databases, start with PostgreSQL. You document everything, then once you have evidence that you need a better database, then you migrate. So you migrate with evidence, not vibes. So one final thought before I hand over to Vadim. So go build something, but pick the boring option first. The best vector database is the one you're not thinking about at 2 a.m. worrying about the RAM usage and everything. You can sleep better at 2 a.m. if you're using PG Vector, probably. Now, I'll hand over to Vadim.
Yep, thank you. So, Geethu just walked you through the theory behind the vector databases. So we have 3 databases, 3 trade-offs, and 1 framework. And I would like to spend the next few minutes showing you how to apply this framework with the real customers. And here's a bit of context. Statforce is a Munich-based consultancy and software development company, and we work across 4 different areas like data and AI, platform engineering, cloud modernization, process, and security. And our real differentiator is co-creation. So we just don't hand over the slide decks to our customers. We develop the solutions together with the customer team. And we're also an Ivan partner. That's why I'm here tonight, and thanks Ivan for sponsoring this edition of Munich Data Geeks. And the story I'm going to tell you lies within data and AI area. So we have a real customer, a real rec pipeline, and a real world migration story. So a customer is a German information portal operator, and this operator has 17 information portals, and they have a data like articles, contact databases, and some other structured records. And their users come with messy natural language questions around different areas and domains. And the goal was simple. Just have one chatbot, one entry point, so I can come with a question like, find me something across all different 17 portals. And for rec, probably one of the easiest solutions is just to use Azure Cloud. And that's what we actually did in the first step. So we implemented the whole pipeline in Azure. The customers were really satisfied with that. But then a couple of months later, they came to us saying, take Azure off. Let's make everything locally on premise. And I would say in 2026, when everyone else is migrating to the cloud, the migration back in the opposite direction, maybe it's a weird choice. And you might ask the question, why? So there are 3 forces, but all pointing into the same direction. So the first one was surprisingly customization. So Azure AI gave them very limited control of how the retrieval was built or how the chunking worked and the orchestration was implemented. So every experiment like different chunking size or chunking strategy or retrieval volume, it was difficult to test it or even impossible in Azure. Besides, the search orchestrator microservices are black boxes. You cannot control them. And at the same time, the local solution gives them the full flexibility and additional point, there is less vendor login. The second reason is predictable costs. Having the local solution reduces the costs that are needed for the Azure, because the Azure solution includes the Azure search, the Azure blob storage, and additional services for running the orchestration. And here, we were able to reduce the costs by using the hardware that the client already had. And last but not least, the ops familiarity. So the IT team of the customer, they already had the expertise, the Postgres expertise, and they wanted to run everything in Docker on the Windows server. So there is no new system to learn or to maintain. So the question became, what is actually the right stack to use here? And in this case, we decided to apply the Geethu framework we saw with you a couple of minutes before. So we have three questions. Again, how many vectors do we have? So today and in 12 months, I would say comfortably under 1 million. We actually expect around 25,000 chunks. And using a dedicated vector base like ClickHouse or OpenSearch, we will just use the resources for nothing. That's why the Postgres is well within its comfort zone. Then, do the queries combine vectors with metadata filtering? And this is not initially, and we decided to keep it simple and add filtering layer later on top. Exactly what Geethu mentioned before as well. And the last question is, how much operational overhead can the client's team absorb? And the honest answer from our side is none, because the capacity of the client is actually the bottleneck. Adding a new system means that there is another thing to monitor, to back up, and to keep on call. And this was not viable for our clients. And the framework that we saw with you before pointed us directly to the Postgres with PG vector. And as I mentioned, there is no new system, no vendor to take care of. And here you can see how the whole things work together, and I would say it's a classical RAG pipeline. So the user asks a question, and then the question is being sent through the front end of the chatbot to the orchestrator microservice that is running in Docker on the pretty old Windows service of the clients. And then this microservice is sending a search request to the retrieval microservice that checks or extracts the relevant information from our knowledge base, which is basically PG vector. And then the retrieved chunks are coming back through the retrieval microservice to the orchestrator. Afterwards, the orchestrator packs their retrieved chunks together with the user request and send it to the Azure OpenAI model that we have. And currently, this is the only cloud dependency we have in this solution. And after everything is being extracted, all of the data is being sent back to the user through the orchestrator microservice and the front end of the chatbot. And underneath of it, I hope you can see it, we also have a monitoring and model tracing layer. So basically, every prompt, every response, every retrieval is being logged. This is really critical for debugging and also for the customer's compliance story. And the big change versus what we had before, all the texts, all of the extracted vectors, everything is being stored in a single Postgres instance. Because before we had Azure AI Search and Azure Blob Storage. It means 2 billing clients, 2 services to maintain. And now we just have a single one. And additional node, only the query and the chunks leave the building of the client. The whole data is still being stored as the client's infrastructure and never leaves the house. So how does the data actually get in? So we have the first tab where we extract the information from portal websites and client databases. As I mentioned before, we have 17 portals with different schemas, different conventions, and the consolidation alone took a lot of time. Then we do a pretty classical step like cleaning. We remove all of the line breaks, white spaces, and weird Unicode characters that were from the old legacy content. And this is a step that nobody talks about, but still everyone has to do. Afterwards, we chunk the whole data. And for this setup, we already took the steps that we did with Azure. We took 256 tokens with 25 overlap, with the eye towards the future optimization through semantic chunking. And in the end, we used embedding model from OpenAI and HNSV indexing in pgvector. And as you can see, in total, we had roughly 3,500 source documents. And generally, this is not a lot of data. That's why pgvector is the best fit here. As I mentioned before, using ClickHouse for such a small amount of data, it just doesn't worth it and will increase the costs. So there are 3 knobs we had to set, and each with a real trade-off. So the first one is indexing algorithm. As Geethu mentioned before, HNSV builds slow, but queries fast. And this is not a problem for us because our content changes periodically and rebuilds happen over the night. We just don't care about the build costs. The only thing we care about is the query latency because this is what the user sees. If it's super slow, they won't communicate with the chatbot. Then the embedding model. As I mentioned before, we opted for OpenAI embedding model basically for 2 reasons. First of all, this is a multilingual model. What we saw from our experience, German users tend to mix English words into the requests, and this model can handle it pretty good. And then this model looks for the meanings rather than for the keywords. One quick side note, we also tried open source models to reduce the costs. Benchmarks were good, but when we saw it in the production, it didn't extract the information that we needed. And the last thing is metadata filtering. We are currently implementing it, and this is the logical next step that we have to do in order to have a functional rec pipeline. So, 3 things, additional things to remember tomorrow after the Munich Data Geeks event. The first one is pgvector wasn't optimal. It was the right solution for the customer. And you should understand the difference. There is a best, like a word best for the benchmark, but there is also a right word that is used for the production. So pgvector fits the client scale, team, and infrastructure. And that's what basically matters. Then, Geethu also mentioned it before, boring infrastructure lets you ship the solution you would like to have. So every new system you add, you have to maintain it during the night or during the day. And in this case, we added no new service to take care of because the client had already Postgres database before. And finally, a dedicated vector database is basically a scaling decision and not a starting point. So start with what you already have. If you already have a Postgres in your technology stack and the data that you have fits there, then continue using the Postgres. So, to conclude, start simple, instrument, and log everything, because debugging, it takes a lot of time and it's necessary to understand what's not doing right. And don't forget to migrate with evidence.